Hello everyone. In this video, I am going to cover section 2.5, Cartesian vectors, and also section 2.6, addition of Cartesian vectors. Starting with the definition of unit vector. If I have any vector A with a magnitude of A, so be careful with these two different colors. The one that's blue means that it's a vector, and then the one that's black, this one right here, means that it's only referred to the magnitude of the vector. So I take the vector A blue divided by its magnitude, the numerical magnitude of this vector. You will give me the unit vector. What it's doing is that it's going to give me a unit vector. Original vector divided by its own magnitude, we're gonna get a magnitude of 1. And it's also dimensionless, meaning it has no units. Okay, and it also points in the same direction as the original vector. Original vector, I divided by the magnitude of that original vector, but the direction is still the same. Unit vector will still have the same direction as the original vector. Unit vectors in the Cartesian axis system are I, j, and k. They are unit vectors along the positive x, y, and z axis. Next thing is we want to see this vector in this diagram. We have vector A that's showing in blue, okay? And I can project the vector A along the x-axis, the y-axis, and the z-axis, the I, the j, the k direction. So I have the x component AX, and I have the y component AY, and I have the z component AZ for this vector. So a lot of times we're going to needing to project this vector twice. This one, for example, this example that we have on the screen, we're going to first project our vector A onto the xy axis. So flat to the bottom of this to the bottom x and y plane. We're going to project it. You get A prime. So other words, this in this triangle, in this blue triangle, but I'm highlighting in red, in this triangle, okay, we're projecting onto the xy plane. And the part that's projecting to the xy plane is going to be me the A prime. Okay. And in this A prime, looking at the red shaded triangle over here, your A prime square, A prime square plus the AZ square will equal to my original vector A squared, Pythagorean theorem. Okay, 90 degree is right here. And then same thing, next one being if I have this on the xy plane. So let me draw it on the 2D notation. There's your x, there's your y. A prime is here. Here's my A prime. And A prime projected into a y, which is this part from here to here. And then a x is this part right here. Okay, that is the bottom one projected into the 2D diagram. In this one, it tells me that A prime square, which is the hypotenuse, will equal to ax squared plus ay squared. Okay, so then overall, if I put these two together, plug the second equation that I wrote into the first one, that will give me the last equation on the screen. Being said, it's going to show a x squared plus a y squared. This is the a prime square, and then also plus a z squared. That will give me the a squared overall. So it's Pythagorean theorem twice. Direction or orientation of the vector A is defined by the angles alpha, beta, and gamma. These angles are measured between the vector and the positive x, y, and z axis. So, and then also one thing to remember, the range of the value goes from 0 to 180 degree. One more time. So alpha is the angle between ax and the original vector A. Beta is the angle between component AY and the original vector A. And then the gamma is the angle between AZ and the original vector A. Okay, these angles are not independent. They must satisfy this following equation: cosine square alpha, cosine alpha square, plus cosine beta square, plus cosine gamma square equals 1. This equation must be satisfied for these three angles, alpha, beta, and gamma. This result can be derived from the definition of a coordinate direction angle in the unit vector. And we remember we'll talk about the definition of the unit vector and then the formula for finding the unit vector for every single component, ax, ay, and az. You're going to do ax over ay over az over a. And remember what we're dividing on the denominator here is the magnitude of our original vector. So this part gives me the cosine alpha, cosine beta, and cosine gamma. So meaning unit vector written in another way, UA would equal to cosine alpha I plus cosine beta j and cosine gamma k. Once individual factors are written in the Cartesian form, the I, the j, the k component, it is easy. We can easily add or subtract them. Remember vectors, what last video we talked about, they need to be in they're not numerical addition because they are vectors. So we're breaking them down into the x component, y component, and the z component. And then later you can add them. All the I go together, all the j go together, and all the k go together. They are vector additions. Sometimes in the 3D vector information, we will be given the magnitude and the coordinate direction angle, or the magnitude and the projection angle. So keep in mind that whenever we define a vector, we need the magnitude and the direction. Okay, magnitude, how long this thing is, how big this thing is. And then the direction over here talks about the A, and the B here talks about two different ways to define the angle, either the coordinate direction angle or the projection angle. First example, so I have F1 and F2. F1 is projected into the YZ plane. Okay, what it means is that there is no X component on this F1. It's only YZ plane. So when I projected this or break down this F1 into my IJK component, you will have no I component because it's on the YZ plane. Okay, and we talk about this triangle 3, 4, 5. It tells me how slant the angle is, and we can find out the component, Y component, and the Z component. Now, F2 is actually in the air. When we break them down, you will have the X component, Y component, and Z component. So overall, this F2, force F2, we can break it two times. So first one, you're going to look at this triangle here. Okay, this one right here, where your 90-degree is over here. We can break our F2 into the first will be the diagonal of the XY plane plus the vertical, this one right here, will be the FZ component. And then this one right here, the diagonal of the X and Y plane, you can break it further into the X component and the Y component. Okay, so let's take a look. F1. F1 is on the F1 is on the YZ plane. Okay, what it means is that the X component will be a 0 because it's on the YZ plane. And then the Y component, so this F1, all we got to do is break it as if it's in 2D. It really is in one plane already. So we, along the direction of the 3, 4, 5, with a triangle telling me how slant that angle is, we're breaking that into the Fy and Fz component. So there's my I and the J and the K for my F1. F2, like I said, we need to break it twice. First one, we're going to project that F2 into the XY plane. So step number one. F2 is breaking down into F2Z, which is this one. F2Z, you see it's parallel to the Z-axis, this one and this one. Z-axis, and then it's the same direction with my F2Z. So F2Z, using that 45-degree, we can find out what that is. And because it's going down, it's got a negative value. And then F2 prime is the diagonal on that XY plane. Okay, and it's going toward the positive direction both on the x and the y, so f2 prime is positive. Next thing, we're going to break down that f2 prime into the xy plane. So if it's hard to see, again, you can draw it again. So if you have x here, y here, and then our f2 f2 prime is here. Okay, f2 prime. And I'm breaking down that f2 prime into the f2 prime x. Well, if I could skip the prime, sorry. So f2x is just x. But if you want to keep that prime there, it's cool. f2x and then f2y. Okay, so overall, using the sine and the cosine, the 30 degree is in between the f2 prime and the x. So 30 degree is right here in my sketch. It doesn't look like a 30 degree, but 30 degrees right here. 30 degree, one more time, is between f2 prime and the x. And then that means you can use that 30 degree, your sine and your cosine, to get the x value and the y value. So you can look at one of this triangle here using your trig functions and put them down. So there's my ijk component for the f2. Now, if I want to do addition, f1 plus f2, uh, to find out what is the resultant force of these two together, you put all the I together, you put all the J together, and you put all the K together to find out what the resultant force is. No problem. If you want to try it out, pause the video and before you move on. So I have two forces, F1 and F2. F1 projected twice. F2, it's given all the forces between F2 and the three axes. Okay, one more time. So F2, I know the angle between that F2 and the x-axis is 120. And the angle between F2 and y-axis is 45. And the angle between F2 and that z-axis will be 60. I know all the angles. We don't need to project F2 because we know all the angles between F and all the three axes. F1, we will need to project it twice. First one, you project it to the XY plane, which will be this one. Okay. And then you project, so we call this one F1 prime. And then you need to project your F1 prime one more time into the axis and the Y axis. So let's take a look. I feel like F2 will be easier since all the angles that are given to you. So let's go take a look at F2 first. We know all our angles. Look at that. Cosine 120, cosine 45, cosine 60. We plug them in, and that will give me the F2 value of F2 in the IJK component. And again, be careful with the direction. Okay. The I component is negative. The reason your I component is negative because it's 120 degree. It's pointing toward the paper, toward that YZ plane. So it's negative 200I, and you have your J, have your K, J and K are positive. And again, really that cosine 120 is a negative value. So when you plug it in, the sign already take care of it yourself. So, but knowing, what actually physically what's going on will help you determine, hey, did I do the sign correctly? And then over here, you have 1Z uh, and one, so projecting your F, right, F1 first time projected into the XY plane, right? You have 1Z going vertical because your Z axis is vertical, and then your F prime being the diagonal of your that's on the XY plane. And be careful with the sign, be careful with the sign. We need to judge the sign. So it's going down, the Z component is going down. You'll have a negative value for the Z, and then the F prime is going to be positive because it's going toward the positive direction of your X and your Y. So you'll have the sine 35 degree and the cosine 35 degree. It's 35 degree because 35 degree is defined from the F1, the angle between the F1 and the XY plane. Okay, so that's how we're using that angle. So in this triangle, in this red triangle that we shaded, if you want to put it in the 2D, F1 is right here. This one is your F1. And then FZ is this one, okay, or this one, same thing. This is your FZ, okay? And this one that's projected to the XY plane, that's going to be my F prime. FZ is that one. In the shaded triangle over here, it's also this end of the triangle as well. And then your 35 degree is right here. Okay, hope that helps you. Broke them down into F1z and the F prime. And then further, let me use a different color. Let me use green. Further, if I am going to break down that F1 further, so X and Y plane is over here. Here's your X, here's your Y. We're breaking that into F1 prime become the diagonal of the vector on your when you're breaking down into the x component and the y component. So your fx is this one, your fy is this portion. Okay. And then if you're looking at any one of this triangle, if you will prefer looking at this one, cool. But the one below, it's also cool as well, meaning this part is going to be my fx. Now looking at the angle, this angle 25 degree is in between f prime and y. Okay, one more time. This angle 25 degree is in between the angle f prime and y, which 25 is right here, 25 degree. And then you use your sine and your cosine of that 25 degree. We can find our f1 f1x in the f1y component. Okay, hope that helps you. Now, with them, all of them broken down into the ijk component, we can put them together doing the addition, find out what is the resultant vector, force vector overall by putting all the I together, putting all the j together, and putting all the k together. So vertically, okay, putting that together, that will give you the ijk. And using the Pythagorean theorem overall for the resultant force, Pythagorean theorem, this gives me the magnitude of the resultant force overall. And also over here, you have your alpha, your beta, and your gamma for the resultant force overall. So you take the x component of the resultant force divided by the magnitude of the resultant force overall. That gives me the cosine value of that alpha. And you do a cosine inverse, that gives me the actual angle of alpha. And you do the same thing for the beta and the gamma. Beta is the angle between the y component and the resultant force. Gamma is between the z component and the resultant force. Okay, I hope that helps you. This is what I want to cover for section 2.5 and 2.6.